this fourth and final video chapter on hydrothermal associations, I want to look at giant gypsum crystals formed either by mixing with hydrothermal waters or in the mixing zone between hydrothermal and phreatic meteoric waters, where we've created giant gypsum crystals up to 11 meters long. And they're characterized by very slow and steady gentle growth over timeframes of up to 1 million years to form these huge crystals. But once again, these are crystals not forming via the processes of solar evaporation. They're forming via long-term oscillations of the brine chemistry around the gypsum-anhydrite precipitation solubility fields. So let's look first of all at the Naica gypsum caverns in Mexico, where we have these giant crystal meshworks that were discovered in the year 2000 in a lead-zinc-silver mine. And we'll focus in on the Cave of Crystals, where we found giant faceted and transparent single gypsum crystals as long as 11 meters in what was a cavern in the Cave of Crystals that was 109 meters long. And the gypsum, prior to the pumping down to allow mine access, was still precipitating on the mine walls. And it was, as I said, first discovered in the year 2000 after the water was pumped out to allow mining access to that level. And so the phreatic cavern system, which was filling these waters with temperatures of around 58 degrees centigrade, was pumped out. Now, the key thing here is the conditions. Before it was pumped down, the cave was water-filled, it was phreatic, and it had temperatures in excess of 58 degrees centigrade or 136 degrees Fahrenheit. After it was pumped out, the pumped out cavern, maintained a temperature pretty constant of around 58 degrees centigrade. And it had something like 90 to 99% humidity, which meant it was a pretty uncomfortable place to access, and certainly without cooling, what they called ice suits, and breathing apparatus. You'd last about 10 to 15 minutes before you collapse from heat exhaustion. I mean, that level of humidity makes your lungs highly inefficient in terms of the ability to breathe. To study these crystals, researchers had to wear suits that allowed the body to maintain a lower temperature and also some breathing apparatus. The cavern was accessible for study until October 2015 when the operation moved on and the cave was allowed to reflood. Human access was restricted after about 2010 because of the damage that too many people going into these caverns was doing. Their formation is related to hydrothermal circulation, supplying water saturated with respect to sulfides, and we had a mixing with cooler oxygenated surface water, which raised the mineral saturated heater water temperature, but the two didn't mix because of their difference in density. But as the oxygen diffused into that heated water in the cavern and oxidized the sulfates into sulfate, that then precipitated anhydrite. Then when the anhydrite-filled cavern, the temperature started to drop, the anhydrite dissolved, but it maintained that temperature at around the stability transition between anhydrite and gypsum at around 60 degrees centigrade. So anhydrite was dissolved and gypsum grew as giant crystals, long and slow, taking up to at least 500,000 to 1 million years to start to infill those warm water-filled caverns. Those huge crystals grew only slowly at very low supersaturation levels from warm phreatic waters with temperatures that were maintained at around 60 degrees centigrade near the gypsum anhydrite stability boundary. If we look at the sulphur and the oxygen isotopes, as we will shortly, the compositions of the gypsum are compatible with its growth from solutions that resulted from the dissolution of anhydrite. And the anhydrite was previously precipitated during typical hydrothermal precipitation via retrograde processes in what was a volcanogenic carbonate matrix. These crystals straddle the notions and the chemistry of hydrothermal anhydrite and gypsum forming in interfaces of brine mixing. Now the mine formed above what was a magma chamber 3 to 5 kilometers below the actual Cave of Crystals. The cave itself is situated on the Naica fault. There's a shallower cave called the Cave of Swords, Espades, a little shallower, 140 meters above the level of the Cave of Crystals, once again filled with large crystals. The green there is outlining the shape of the lead-zinc-silver ore body. It's a silver mine. You can see the pump down level indicated by the dashed line, allowing access to those caves. So when it was forming, we had cool, oxygenated, meteoric-phreatic water in contact with what were rising, mineral-saturated hydrothermal waters, but because of the density contrast between the more saline hydrothermal waters and the fresher meteoric waters, the two didn't mix. They were density stratified. So as that happened, oxygen was slowly diffusing into the heater water, and it's oxidizing the sulfides into sulfates. That then created the precipitation of anhydrite in what is a Cretaceous limestone host. When the overall temperature of the waters filling the cavern started to drop below 56 degrees, we moved out of the stability field for anhydrite. We started to dissolve that hydrothermal anhydrite. But at the same time, because we're hovering around the gypsum saturation temperatures, gypsum started to precipitate. You can see that both in terms of the brine inclusions and its isotopes. These giant gypsum crystals came from what were low salinity solutions at temperatures of around 54 degrees centigrade, shown in green in the upper curve, which is slightly below the solubility dissolution temperature of anhydrite at 58 degrees centigrade. We had very slow gypsum growth occurring in the phreatic caverns when the waters were around 55 degrees centigrade. At a temperature of 55 degrees centigrade, to form the volume of gypsum in that cavern, it would have taken about 1 billion years to grow crystals to 1 meter in diameter. If it was a little bit warmer, 56 degrees, once again, slow and steady, that same crystal size, that meter diameter, would have formed in a little less than half that time, at around 500,000 years. We are characterizing the growth in this situation, as you can see, by the mixing trend of the two fluids. We have the mixing line between the high salinity waters and the deep phreatic thermal waters. As those two solutions mix, this is typical mixing chemistry, saturation shown in the yellow, under saturation with respect to gypsum in the blue, we can see we move as we have those waters mixing into the gypsum supersaturation field. So we have a mixing of deep, warm, moderate salinity waters with less saline, meteoric-phreatic waters at temperatures that hovered around 56 to 58 degrees centigrade. So what do we call this? Is this a hydrothermal product or a mixing zone product? It's a mixing zone product associated with mixing with hot hydrothermal sulfide-rich waters. Okay, let's look at a second example now of giant gypsum crystals. Not in a cavity, but in an actual replacement process in what is the world's largest known geode. This is the Pulpi geode in the former Mina Rica mine in Spain. This gypsum, these clear selenite crystals of gypsum, have formed an 11 cubic meter ovid cavity. It's a geode. A big one, but it's a geode, with walls that are now covered with meter-sized, idiomorphic and highly transparent gypsum in the form of clear gypsum known as selenite, where the crystals grew from a calcium sulfate solution at what were very low supersaturation values. The small number of large crystals within the geode and their homogeneous size lining the walls of the geode once again indicate an ultra-slow nucleation where waters were derived with low supersaturation values being maintained for a long time without significant fluctuations in chemistry or temperature. The longer crystals that characterize the floor of the geode, in other words, the gravitational crystals, also grew under the same conditions isotopically as the blocky crystals that line the lateral and upper walls of that geode. So this is a very homogeneous gypsum crystal population. If we look at the homogenization temperatures that we get from the analysis of those selenite crystals and their inclusions, we can see that the growth temperature was actually much cooler than the phase transition temperature we saw in Naica, where we had temperatures of around 58 degrees centigrade. They were even colder than the maximum solubility temperature of 45 degrees of gypsum. We can see that they're down in the low to mid-20s for the dominant inclusion temperatures captured by those brine inclusions in those selenite crystals. So the formation of the Pulpi crystals, these large crystals in Pulpi, were based on a very slow cooling rate, which didn't be associated with the anhydrite gypsum transition temperatures of 56 to 58 degrees. Rather, the growth of the crystals in the Pulpi geode was the result of what was a self-feeding mechanism, creating isovolumetric anhydrite replacement via gypsum at a temperature of around 20 degrees plus or minus 5 degrees centigrade. There was probably also an episodic ripening process that was enhanced by the temperature oscillations. I mean, you can see similar crystals in Triassic lead-zinc deposits where we have gypsum replacing anhydrite with that uplift and that meteoric overprint across much of Spain. We are seeing a system which is characterized by isolation and slow growth in both Pulpi and in Naica, but quite distinct temperature and crystal growth mechanisms. The Pulpi gypsum replaces anhydrite at a low subsurface temperature, 28 degrees, while the Naica gypsum grew into a warmer phreatic cavity soon after the precursor anhydrite dissolved. Both are the result of anhydrite rehydration In one case, Naica, we're growing crystals in a cavity created by prior dissolution of anhydrite. In pulpy, we are seeing a replacement of anhydrite by gypsum at lower temperatures. So, two giant crystals, slightly different processes of formation. Both processes are the result of uplift of a hydrothermal system into a zone of mixing with the deeply circulating meteoric-phreatic. In other words, migration into the telogenetic zone. So these giant crystals that we're looking at are the result of telogenesis in a sulfide-rich system. Okay, so let's step back and have an overview now of what we've talked about for non-solar evaporite salts. We can see that ionic saline minerals, like the various calcium and sodium sulfates and chlorides, and another much broader variety of mixed salts, don't necessarily have to form by brine concentration driven by solar evaporation. So we have a whole range of ionic salts which are non-solar evaporite derived, non-evaporite salts. Typically, those salts are brine sourced, and the precipitates have the mineralogy with the same name and the mineral structures, anhydrite, halite, glauberite, bischofite, but they're not true evaporites. The mother brines were not the result of solar evaporation on the Earth's surface. The mother brines came from various forms of magmatism or shallow brine mixing interfaces, or even cryogenesis, which we'll talk about in the next module. And all of these settings are capable of forming significant combinations of prograde and retrograde salt volumes, but they are not true evaporites.